Another way that waves can bend is called refraction, and refraction is a bending of a wave as it changes speed. You've experienced gradual refraction before, I'm sure. For example, if you have ever been at a lake on a nice cool summer night, and you can really hear the people across the lake very well. Typically, their voices would have carried off into the atmosphere, and there wouldn't have been enough sound intensity to hear it on the far side. But when you have that nice, cool water, the air is trying to go this way. But one side of the air is getting slowed down and the other side is not. And the slowed down part, it's sort of like catching your tires in sand. It turns you. Well, the wave gets turned too, and it can bend down to the other side of the lake where you can hear it very well. And by the way, that does mean that particles can diffract as well. Particles can hit and bend like that. Now, waves are not solid objects, so the analogy only goes so far. We'll get into that later with something called Huygens principle. But for now, you can think of a wave as almost like a little mini car. If it's driving along and then one tire slows down, that's going to cause it to turn in the direction it slowed down. That is refraction. You've seen light refraction before too. On a very hot summer day, you have a mirage. Now, have you ever seen a mirage? You probably have. In a car, sometimes you'll see the road shimmering in front of you. It actually looks like water on the ground. What's going on there is the light is coming down from the sky, and before it has a chance to hit the ground, it's bending upward from refraction and hitting your eye. Your brain says, oh, the light came from a straight line that way. That's sky on the ground. And what do we think of when we see blue sky on the ground? We think of water. And so our brain says, aha, that's water, when really you're looking at the sky through a bent light wave. Now, diffraction can happen abruptly as well, oftentimes when a wave changes medium. So for example, when light goes from air into water, the light will actually bend. So for example, this is a classic example. Our pencil looks bent when clearly it's not bent, it's still straight. But in the water, it looks bent. And the reason is, again, because our brains always think that light travels in straight lines. So we're able to be tricked to some degree by refraction. This abrupt bending of light as it changes from one medium to another is pretty important. And there's some math that goes along with it that both classes are going to have to know. But before we get to that, let's talk about why light in particular slows down. And you're going to have to memorize two reasons. And both of those reasons are something I am going to test you on. So make sure you memorize these. The macroscopic answer, meaning like the zoomed out answer, is that when light enters a new medium, even though it doesn't require a medium to travel, it can move through empty space. When it enters a medium, its wavelength gets shorter, but its frequency stays the same. Remember, velocity is frequency times wavelength. If you've got the same number of waves passing by each second, but those waves are shorter, then they must be going slower. So the wavelength shortens, the frequency stays the same, is the macroscopic answer. But if we zoom way in, we get a different answer. We get the microscopic answer. So the microscopic answer is this. When light comes in and hits a particle, it excites an electron in that atom or molecule, and that energy that was the light is no longer light. It's not moving at all. It's now the excitation energy of that electron. That makes the electron unstable, so after a split second, that electron falls back to a lower energy level and re-emits that energy in the form of light identical to what it absorbed to excite it. That hits the next electron, and the process repeats. And so light gets passed like a game of hot potato from atom to atom to atom to atom to atom all the way through. And it's, even though in between each atom, it's traveling at exactly the speed of light, it spends some of its time as not light. The energy transforms to another type. And so the average speed goes down. The longer those atoms or molecules hold on to the light on average, the lower the average speed of light in that material. You have to know both of those, so make sure you memorize them. The macroscopic answer is shorter wavelength, same frequency. The microscopic answer is molecular hot potato. But you're not allowed to put molecular hot potato on a test. You've got to explain it better than that, all right? How fast light travels in a material depends on a property that we call the optical density. It has nothing whatsoever to do with actual density. So, optical density is how thick the material appears. Air has an optical density of 1 by definition. A vacuum, air is actually very slightly more than 1, which is important for sunsets and things like that. We'll talk about that a little bit later. A vacuum is exactly 1. Air is close enough to 1, that's what we're going to use. But something like lucite, which is kind of like plexiglass, it appears thicker than regular air. And that lucite it's got an optical density that's higher, probably something around 1.5. How do we define this? Well, it's represented by a number we call the index of refraction. It's represented by a lowercase n, and the definition of the index of refraction is the speed of light divided by the speed of light in that material. So the speed of light in a vacuum, c, divided by the speed of light in the material, v. That means it's velocity over velocity, it's unitless, it is a ratio, and because the speed of light in a vacuum is as fast as anything in the universe can go, that means that it's always equal to or greater than 1. This bending, by the way, is why we can see transparent objects at all, ignoring the fact that they're a little dirty. If you look at these, you can see that there is a beaker inside the other beaker, right? But if we take a substance like corn oil that has the same index of refraction as Pyrex glass, and we fill it, watch what happens. Vanishes. It's gone. It's not really gone, of course, it's still there. We just can't see it because the light doesn't bend when it hits the inner surface of the glass. Pretty neat, huh? So anyway, if you have two materials with different indices of refraction, the ratio of those two indices of refraction is the ratio of the velocities of light in them. And because of the macroscopic explanation of why light slows down, you get velocity is f lambda, frequencies stay the same, the f's cancel, it's the ratio of the wavelengths. If they have a relative index of refraction of 1, if that ratio is the same, then there's going to be no bending of light and you're going to get something cool like you just saw. By the way, sunsets take longer because of refraction as well. I mentioned the index of refraction of air is just slightly higher than 1. The light coming from the sun actually gets bent around the earth and hits our eyes after the sun has dipped below the horizon. So when we think the sun is right on the horizon, it's actually just slightly below. This math of abrupt refraction from the changing of mediums is called Snell's law. It's named after Willibrord Snellius. There was some argument about who discovered this law first. Snellius said he did, and yet Descartes published it first, although it wasn't discovered in English yet because Descartes was French. And so Descartes and Snell, there was some argument about who should get credit. Although it turned out that years later, there's some pretty good evidence that Descartes probably read Snell's work and basically just plagiarized it. Now the French say, no, that did not happen. So for a long time, the English-speaking world called it Snell's law, while the French called it Descartes' law. And after that evidence came out, the French were like, okay, fine, we call it the Snell-Descartes law, or the Descartes-Snell law. And all of this is ridiculous because we're arguing about a couple of decades difference between these two white European men when 800 years earlier, Abu Sa'ad al-Ala ibn Sahl had published it in Arabic. So we really should call it Ibn Sahl's law, but we don't. We call it Snell's law. Regardless, what does Snell's law say? It's a mathematical law. It says n1 sine theta 1 equals n2 sine theta 2. n1 and theta 1 are the index of refraction and angle in the first medium, and then same thing with the second medium. So as an example, suppose we have a beam of light that's coming in and hitting some crown glass from air. If the angle of incidence is 40 degrees, what's the angle of refraction? All we have to do is plug in. So here we go.
So we start with Snell's law, n1 sine theta 1 equals n2 sine theta 2. Index of refraction of air is 1, angle is 40 degrees, index of refraction of crown glass is 1.52. Plug in and solve, we get theta 2 is 25 degrees. Note that this means that theta 3 is also 25 degrees because they're alternate interior angles of parallel lines cut by a transversal. So we could do Snell's law again and really create a chain of n1 sine theta 1 equals n2 sine theta 2 equals n3 sine theta 3 equals n4 sine theta 4, realizing that some of these indexes of refraction are the same and canceling, and we get theta 1 equals theta 4. Anytime you have a light ray that enters into a block that has been cut parallel, when it exits, that exit will be at the same angle. It will be parallel to the incident ray. Note that this is why windows just don't distort things very much unless the window itself is warped or curved.
Pretty easy, right? We can make that a lot more interesting by using curved glass and things, and we can make things really interesting, but lenses and things, that's a topic for another video. That analogy I used earlier for refraction of treating light kind of like it's a car driving along. So when this car is driving along and one wheel hits, that changes the direction of the car until the second wheel hits, at which point it just travels that lower speed, right? Well, if we apply that on the other side, if the car is traveling along in, say, a muddy substance and it's going slow, and then it hits pavement, the first wheel speeds up and it's going to bend away from the normal until the second wheel hits, and then it's going to travel out. Well, what happens if it speeds up so much that the car actually loops all the way around before the other wheel even has a chance of coming out? It actually reflects instead of refracting. It will reflect if the angle is extreme enough compared to how much it speeds up or slows down. So this is called total internal reflection. And I've tried 6 times to get a good video of it, but I've got a cool demo that I can show you in person of a piece of clear glass acting like a mirror because of total internal reflection, and I will show you that. But anyway, when we're doing Snell's law for a beam of light that is traveling in a medium with a higher index of refraction, and so it's going slower, and it hits a medium with a lower index of refraction, it can reflect in. It can actually hit and then bend to exactly 90 degrees and travel straight along the side. If that happens, that's called the critical angle. And finding the critical angle is super easy. It's Snell's law, n1 sine theta 1 equals n2 sine theta 2. If theta 1 is the critical angle, theta 2 is 90, and the sine of 90 is 1. So the sine of the critical angle is just equal to n2 over n1. Don't memorize that. Know the idea and apply Snell's law. n1 sine of critical angle has to equal n2 sine 90. If the angle theta 1 is bigger than the critical angle for the two materials you're talking about, instead of refracting outward, it will reflect in following the law of reflection. Angle of incidence equals angle of reflection. This idea of total internal reflection is extremely useful in fiber optics, where we send light down a fiber that we can bend in all sorts of ways, and it will ricochet its way down that fiber, continuously reflecting back inside. And so we can make flexible glass in Corning, New York, for example, and we can use that flexible glass with as high an index of refraction as possible, and then encase it in another glass with as low as an index of refraction as possible, so that the vast majority of the light gets trapped inside that central piece of glass. And that fiber optics allows us to send light at extraordinary speeds from point A to point B, and it's one of the things that allows cable television and the modern internet to actually exist. And by the way, a lot of common indices of refraction are on the Regents reference tables. You can just look them up here. AP, you'll have to find them in the book, or if you need them for a problem, either that's the thing you're supposed to be solving for, so you won't need it, or it will be given to you. One last note. You see how on the reference tables it specifies for these indices of refraction a frequency of 5.09 times 10 to the 14 hertz? That is the frequency that is dead in the middle of visible light. For your rainbow Roy G. Biv, it's right in the middle. It's this color. Now, the reason why they have to specify that is because light actually bends more if it's higher frequency. It's got a higher index of refraction. And so the index of refraction is an average for visible light. So lucite, we say it has 1.50. Well, that's for this color. But for blue, it's a little bit higher. And for red, it's a little bit lower. So interestingly, if we can shine light through a substance, white light, made up of all of the colors of the rainbow, What comes out the other side can actually be spread out a little bit. It's called dispersion. Dispersion is the separation of white light into its component colors. Or at least, it doesn't have to be white, it's got to be polychromatic light, light of more than one color, rather than monochromatic light, light of only one color. Shining polychromatic light through a substance when it hits at an angle will cause the colors to separate. That's dispersion. Know it. So those are the first two ways that light can bend. There is a third way we're going to deal with, but we're going to look at it later. In the meantime, we're going to take a break from that, and in the next video, we're going to talk about the phenomenon of interference.